Welcome back to another Computational Thursday. I asked you for your thoughts on how we go about making room for computation in the curriculum, and several of you have responded. Ian Schroeder says that he has two questions that come to mind. Staff who are teaching but have no exposure to computing, how do we help them? Yes, absolutely we need faculty training, because almost none of us that are in the professoriate right now had this when we were undergrads, right? A lot of the things we do, clickers, just-in-time teaching, flipped classroom, all of that stuff, most of us did not have when we were undergrads. And so we're a lot of these engaged learning practices, we're being asked to teach using techniques and tools that we didn't have exposure to. And it's going to be really neat when the folks who had that in undergrad start to graduate with their PhDs, start to get into faculty positions and start to teach based on their experience as undergrads. And they are starting to do that. You are starting to see that with recent incoming generations of faculty who actually experience these things. And it's really interesting to watch them in the classroom and see their take on it, see them make little modifications to it, and to see what they come up with that they'll then need to train themselves on, which is great. Where I think computation kind of is a little bit different there, because I see a lot more people willing to try pedagogical stuff than trying computation, because we have computation is so tied to our research avenue, right? I mean, the number one thing you see in people adopting computation is that they did some computation in their research, and so they go to incorporate it into their course, the same way a theorist would incorporate some great problem solving, and an experimentalist would incorporate some great lab techniques. Those of us with computational research backgrounds want to incorporate that because, number one, we want the students to be trained to do the stuff that we weren't trained to do. Number two, so that we can train them so that they're interested in it, we can recruit them to our research groups, but also because we understand that it makes for a more holistic physics learning experience. And anytime you can invest something you're doing into your class, it's a really good opportunity to connect with the students, show them some authentic experiences. So yeah, absolutely, we need faculty training. But I also think it's important to establish what level of proficiency an instructor needs to have. And again, I go back to the comparison with labs. So I have a PhD in computational kind of theoretical condensed matter physics. I am not an experimentalist. I am a disaster in the lab. I feel like my lab students get a little bit shortchanged because I'm always like, oh, and then you have to calculate the, what's it called? The systematic uncertainty in this. And they'll say, oh, but the lab manual says systematic uncertainty and statistical uncertainty. What's the difference? I don't know, because I never used that. I've never once used that lab terminology stuff in my professional discipline, nor should I have to, right? Just like an experimentalist should not have to know the difference between LAPAC and scale APAC, because that's a computational thing. That's on my end to understand. But that's not the level of proficiency that we're talking about. We're not talking about needing a PhD in computational physics in order to teach computation. Again, go back to labs. When I need to teach that stuff, when I need to teach them about how to propagate uncertainty, when I need to teach them about how to evaluate the instrumental uncertainty, or how to evaluate the R-squared value on a slope, I'm not talking about PhD level experimental stuff. I'm talking about freshman level experimental stuff. And yeah, I have to go back and remind myself of that. But I do that, and I do it just before I need it, right? I don't spend my summers reviewing all of the experimental techniques. I do that, a day or two before I'm supposed to teach it in lab. And I think we can do something similar with computation. I think we can get people a decent base of computational knowledge, and then we can get them material that gives them a reminder just before they teach it, so that they have some idea of what the students are working with. Because if you give the students a starter code And if you give them some materials, like a Let's Code Physics video, to give them an overview, you're not really there to teach them the computation from scratch. You're there to proctor the computational activity, just like I'm there to proctor a lab. And I think if we can kind of get into that mindset, I think that would be very, very helpful. So where do you go to get that training? Well, Let's Code Physics is a wonderful start. But if you're looking for something more interactive, I cannot recommend highly enough a Pickup workshop. Pickup offers workshops throughout the year. Usually we have a big one over the summer with workshops for new faculty. We also usually have some sort of workshop or session at AAPT meetings. You can also go to the Pickup website, join the Pickup Slack, and just ask people, what do I need to do to get started? What's a good activity for me to try out as a first-time computational integrator? You can even reach out to individuals in Pickup. We are always more than happy to share the good word of integrating computation, where most of us are more than happy to, carve out an hour here or there to, give you an overview, walk you through an exercise set. We also have a webinar every month to kind of go over issues in integrating computation. And those webinars, even if the topic is not necessarily of interest to you, the conversations afterwards are incredibly invaluable. And remember, the thing we're aiming for is that minimum level of proficiency. We really only have a couple of tricks in our computational activities. It's usually some form of numerical integration. So if you can understand how a Riemann sum works, you can teach your students computation. You just show them the math, remind them of what a Riemann sum is, or if they've never seen it, kind of walk them through the process of adding up tiny pieces to get a whole. And then you show them how it works out in the code, and what they're doing after that is they're using the code. They're not writing it from scratch. They're not deconstructing it to find out how every little detail works. They're trying to use it because the goal is to teach them the physics. And so if you keep in mind that minimum proficiency that you need and that the goal is to teach them the physics, I think you can go pretty far. Ian's second comment, I love this. Make the circle bigger. Computation does not belong to physics solely. We need to get chemistry, math, and biology to start integrating computation as well. Yes, amen. You'll get no argument about that from me. There is some level of effort being exerted in chem and bio and math to do this. I know in chemistry they do have some vein of computational integration in chemistry, which admittedly I have not looked into. I just saw a couple of articles that it was a thing, but I haven't really looked into it. Math is doing this. Math does a very good job of getting students on board with things like Desmos, because I see students coming into Physics 1 now, and they're using Desmos spontaneously without being told to go do this on a computer, which is really cool, right? Because that's the thing we want to see is students using these tools because they value them and not because they're being told to use them. Biology, I'm not as aware, but I'm also not as connected with the even tenuously with biology education. But I do know that in the physics efforts for introductory physics for life sciences, or living physics, as I think is being branded now, they are working on integrating some computational activities that do tie into the biology side of it. But yeah, absolutely. I would love at some point in the future to start releasing some chemistry, math, and bio-related videos on this channel. I just need to get myself immersed in the content and find out what would be a relevant, accessible topic to the intro-level audience there. Next comment comes to us from Zach's lab, where Zach is talking about how the pandemic made them basically flip their classroom in emergency mode, but it's turned out to work out very well and is another good way to make room for computation. So another way you can make room for computation, throw out the lecture, right? I mean, the reason we think we don't have time for these cool activities is because we think we have to go to the board and walk the students through each problem, each derivation step by step. That is what at-home time is for, because that's what their textbook's for. That's what videos are for. You know, if all they're going to do is take in information, let them do that on their own time. Your precious time with them in class needs to be reserved for interactive activities where you can give them feedback. And computation is a wonderful way to do that, because the students, they're building out this model in parallel with building out their understanding. And the computer is there to give them some of that feedback that they need of things like, nope, you're trying to add a vector and a scalar, or you're getting a flat line instead of a sine curve because you forgot to change the force from a positive to, or from a constant to a linear force, And so, yeah, I don't think it's an accident that we have computation and reformed engaged learning practices kind of going hand in hand, because they both have the goal of having the students learn the material by working with the material. And I think that's really important. And I think that those two things together, so things like clickers, just-in-time teaching, flipped classroom, etc., I think pairs really well with computation, because you want to have an active classroom. Well, what activity are they going to do? A computational activity is a great thing for them to do there. Last comment comes from Blick19933. As a concerned parent and grandparent, as well as volunteer tech instructor at a local public library, thank you for your service. I have thought we are doing CS the wrong way in our public schools. Our district and others in our area have CS pathways that don't really teach code. Can I add to this? I've always been surprised. This has not been every CS student, so I'm not painting with a very broad brush, but it has happened more than once that a CS student comes into my class, finds out we're doing programming, and says, "Oh, I'm a CS major. I know how to program." And I say, "Okay, great. So you know how to set up a for loop, right?" And they look at me and say, "A what now?" Because they're not learning programming, right? They're learning website development and database management, which are important, which are wonderful. We absolutely need those, but they're not necessarily getting into coding, at least not in that first semester, at least not those students that I had a couple of times in class. So again, this is a forum. I welcome feedback from our CS fellows to tell us what to tell us what we're missing there. I believe every student should learn at least the basis of coding, and tools like GlowScript should be added to the physics curriculum. No argument here. I have teens in our library coding classes that say they learn more about coding here than they do in their CS classes. Again, depends on the class, I'm sure, but good for you, Blick. I recently added VPython GlowScript to my own knowledge base, and we're starting a library class teaching it as well. Great, wonderful to hear that. The wonderful thing about VPython GlowScript, I know we geek out about it a lot, and there's a joke that one of the P's in pickup stands for Python. But the amazing thing about GlowScript VPython is that it makes the visualization so much easier. If you try to make a visualization in MATLAB or C++ or C# or whatever you're using, there's so much overhead involved. But with VPython, you just say sphere. There it is in the center of the screen, a sphere, and you can give the sphere a name. And you don't even have to specify its properties yet because of the way the object-oriented programming works. And it's just so wonderful to get students on board with that. And they feel like they're doing something. The fact that it has a visualization and not just a printout, they actually feel like they're doing something. They feel like it's hands-on, like they're doing some sort of experiment, which is key. That's so wonderful. Yeah, I mean, the thing about teaching coding early and teaching it to everybody is that it's not that we expect everybody to be coding, right? That's a naive, limited vision of the future. But a couple things that come to mind is that we don't know who's going to be coding, right? I wouldn't have thought when I was in college that physics involved so much programming because I didn't see anybody doing it. And I certainly didn't think of anybody in biology heading off to do programming. But I mean, think about it. Think about everything we do in STEM that involves computers. It involves telling the computer to do something. And there are some days you just need to tell it directly what to do because the software you have isn't doing it for you. Also, who's going to write that software? Is it really going to be all the CS graduates going to have to learn the bio and the chem and the physics to write a bio, chem, physics software? No, it's going to be the CS folks and the subject matter experts working together to develop that subject-specific code. And who knows? I mean, are we going to have a day where librarians are going to have to code something in their own database? Are we going to come to a point where physicians are having to write a code or working with pandas to keep track of patient records and things like that? We don't know. We literally don't know what these students' career demands are going to entail. And so it's important that we teach these skills. And if the student uses it, great. And if they don't use it, it's not like it's not worthwhile. It's not like it doesn't teach them the critical thinking, the logic, etc. So that's some follow-up to our Computational Thursday about making room for computation. What else do you think? What other topics have we brought up here that you would like to spend some more time on? Have I said anything that glosses over some aspect of these considerations that I need to be more aware of, or that I need to go back and reconsider? Thank you so much for watching. I will see you next time. Bye-bye.